For my materials science project, I chose to do it on a product called petrogel, which is an innovative solution to helping clean oil spills. During the course of this presentation, we'll go over what petrogel is, why it's significant, its various properties and its structural makeup, how it's synthesized and applied, the product history, as well as the impact for the future. So what is petrogel? Basically, it's a synthetic polymer that is oil-based and a pure hydrocarbon. It's created by mixing two polyolefin polymers in the lab and functions to stop the spread of oil spills, as well as absorb and reuse the resulting oil, which is unlike any other type of former solution to oil spills. So why is this product significant? Well, clearly it has quite large environmental implications in terms of preservation, especially in the face of oil spills and the various disasters that can result. The product is able to stop the spread of oil, but it's also able to absorb it out of the ocean, and actually the oil can be reused. It's not just a waste product. It's able to function in a multitude of climates, which prior solutions to petrogel were not always able to do this. And it's actually very cost effective because you can only recover about $85 worth of oil for a total of $16, which is a very reasonable price point. So in this image here, you're able to see how petrogel works. To the image on the left, you can see a large oil spill and how it's able to be contained and condensed to the image on the right by using petrogel. So the properties and structure of petrogel include an interconnected microporous network of hard and soft polymers, as you can see on the image to the right. It has a large surface area, which allows it to have quick interaction with the oil and absorb it more readily. It has a high molecular weight and uniform copolymer composition. It's oil-based, so it readily bonds with the spilled oil, which is important. And it maximally absorbs the oil without absorbing water. This is because it is highly swellable. And as you would imagine, in an oil spill, it's extremely important to be able to remove the oil without taking out too much of the water from the ocean, because that would just be not as efficient. So here is another diagram basically showing that microporous interconnected network. There was a product called petrogel that was the first iteration of petrogel. And as you can see, it is not as interconnected and overlapping, and this basically resulted in it not being able to work as efficiently and absorb as much oil. petrogel is actually able to absorb 2 times as much oil as petrogel was. So how is this synthesized? Basically, there is a reaction that occurs, which is mediated by the Ziegler-Natta catalyst and a two-lane solvent. It's done under nitrogen atmosphere conditions, and it's under constant agitation as it goes through this process. It goes through a specific reaction time and must be under a specific temperature, and then it is terminated by isopropanol. The result is a coagulated polymer, which must be cleaned and weighted, and it is then assessed for copolymer compositions, as well as various molecular weights to make sure that it's the optimal thermal cross-linking properties that result. In terms of its application, petrogel will bind to the oil and create a gel-like substance, which will then float on the surface of the water, and various skimmers are able to skim this off the top of the ocean. So here is the prior reaction that was discussed. As you can see in the bottom image, there is the catalyst that was mentioned, as well as the important step of thermal cross-linking. Here basically shows how it is applied. So the image to the left shows oil on top of the water's surface. It shows the application of iPetrogel and how it creates this gel-like substance, as you can see in image C. This is able to be very easily scooped off, and the result is a crude oil. To the right is what it would look like in the ocean, and these are the skimmers that are used to remove the product off of the ocean surface. So it's important to look at the overall history of oil spills and prior solutions that were given during these crises, so that iPetrogel would be able to offer solutions to some of the problems that still resulted. So in the 2010 Deepwater Horizon spill, only 10% of the oil was recovered and all of it was unusable, so it was complete waste. It resulted in 80,000 tons of solid waste and 200 million gallons of spilled oil. So clearly this cleanup process was not very effective. In the BP oil spill, 60% of the oil was never even accounted for. In this case, underwater oil-eating microorganisms were applied and dispersants were also used in order to try to mitigate the damage. In the 1989 Exxon Valdez spill, or oil spill, the tactic that was used was also microorganisms. However, it was ineffective due to its inability to work in colder Arctic climates. So iPetrogel looked at these shortcomings and was able to offer some solutions. It's specifically tailored for all climates, especially for Alaskan crude oil, and works with cold water spills. It's also able to contain oil spills, so the issue of oil never being accounted for is now not an issue. And it also allows the oil to be reused in the future so that anything that is collected is not gone to waste. So overall, if you looked at the impact for the future, this is huge in terms of preservation of the environment in the face of different disasters, specifically oil spills. It's able to mitigate the devastating impact that they have, and it's able to answer problems that previous solutions could not, such as being able to stop the spread of oil spills, remove it from the ocean, and allow it to be processed for reuse. The ability to be used in all types of climates is also unprecedented, and it's extremely cost effective, which is very important if it's actually going to be a practical implication.